Thank you, Roberto, and let me explain why we are interested in searching for anti-deuteron in space. We know that there are many evidences for dark matter, both from galactic rotational velocity, or from lensing of galactic clusters, or from cosmic microwave background, or from colliding galactic clusters. Merging all these evidences together, cosmology gives a strong indication for a non-baryonic dark matter component in the universe, forming about 25% of the universe content. So, assuming that this particle is a particle beyond standard model and have some interaction with normal matter, we can study for this interaction in three different ways. One is by colliders producing directly the dark matter particle. Another method is to search for elastic scattering of the dark matter into the normal matter. Another possibility is the annihilation of these dark matter particles into normal matter, so producing both matter and antimatter. Then there is a link of cosmic rays with dark matter. Since if this is our galaxy, we know that this possible dark matter annihilation can produce additional source for positron or for antiproton that could move in the galaxy and eventually reach the Earth. But electron and protons are produced by high energy sources such as supernova remnants. And some of these high energy protons would eventually collide with proton in the interstellar medium and producing a pair of antiproton, proton, and other antimatter such as positrons. Then, in general, this is the scenario where we search for an excess, a bump of antimatter produced by dark matter annihilation over a background of secondary antimatter produced by cosmic ray collision. Then the endpoint of the excess of this bump is related to the particle, dark matter particle mass. The amplitude of the peak is related to the annihilation cross-section, and the width of the peak is related on the number of different annihilation channels. And this is exactly the typical shape that AMS have observed into the positron fraction. There is an excess, very big excess of positrons above the expected secondary positron background. Then this excess is very similar to what we expect from dark matter annihilation, but there are also other explanations, for example, astrophysical sources such as nearby pulsar. So in general, this will be addressed by Paolo Zuccon in another talk here at TIFPA. But let me say that it is mandatory to search for dark matter annihilation also in all the other possible channels. And this is the example of antiprotons, where the measured antiproton flux by MS is very similar to the expected secondary background. However, there are many papers that are trying to fit this shape with additional bumps. So some excess of antiprotons in the region of few GeV, or also in the region of 200 GeV. So there is an excess at the level of 3 or 4 sigma above the expected secondary antiproton background. So in some paper we found that there is a robust excess in the cosmic ray antiproton spectrum. But there is a question, because other papers instead say that MS antiprotons are consistent with the secondary astrophysical origin. So this is interesting, because the excess is pointing to cross-sections, annihilation cross-sections that are very near to the expected simple model of thermal annihilation. But the important point is that if these excess are true, we expect also an excess in low energy anti-deuterons. What is an anti-deuteron? Anti-deuteron is a pair of an antineutron and an antiproton. And the binding energy is very, very small. So a secondary anti-deuteron could be produced by high energy protons that are colliding with interstellar medium proton that is at rest. And the antineutron and the antiproton should be produced with a relative momentum that is very, very small. They have to be produced in coalitions. And this coalition is a very rare process. Moreover, to produce an antineutron, an antiproton, and another pair of neutron and proton, you should have an energy threshold larger than 16 GeV. And this is the energy spectra of the primary protons. And so, since this is very steep, the fraction of primary particle with energy larger than 16 GeV is very, very small. Moreover, the anti-deuteron is produced in a system frame that is boosted with the center of mass of the collision. So it's very suppressed, the flux of low energy secondary anti-deuteron. Then this is the expected scenario. And x-axis, we have rigidity, that is momentum divided by charge. Okay, this charge is 1. And then this is the expected flux, in blue, of the anti-deuteron from collision of ordinary cosmic rays. You see that this is very suppressed at a low momentum. Instead, this is the signal that is expected if this bump of antiproton is true, and is expected from dark matter annihilation. So you see that at low energy, we expect a large signal of anti-deuteron from dark matter respect to the astrophysical background. So the current best limit is for anti-deuteron is provided by the best polar 2 experiment, that is a superconductive magnet spectrometer having time of flight counters, having Cherenkov detector. So it's a very complex experiment that have taken data over the Antarctica 10 years ago. And this is typical analysis with a spectrometer. You can select by the deposited energy that a heavy massive particle will deposit at the same rigidity larger energy than the lighter particles. So you select the deuteron, and anti-deuteron. And then you ask for missing Cherenkov signal, since these particles are low, below the Cherenkov threshold. And you can look at rigidity, that is momentum divided charge, as a function of inverse of velocity as measured by time of flight. And then you see in the positive part, tritium, deuteron, protons, and then in the negative, antiprotons, and you are missing from anti-deuterons. So in their analysis, you find a limit in the flux of anti-deuterons of the order of 6 times 10 to the minus 5 in the normal unit of flux. And this is a commensurate improvement with AMS, but at quite larger energy with the aerogel detector. You will find a deuteron, proton, kaons and pions that are produced inside the detector, and antiproton, and this is the window where you will search for anti-deuterons. So you will see that already now the sensitivity of AMS is exceeding the sensitivity of BESS. But let me move to other possible detectors that are not relying on the use of magnetic spectrometer in space. What happens when a low energy anti-deuteron is stopped in the material? This particle is captured by the atoms. And then during the atomic capture, there will be a typical atomic transition. And the X-rays produced by this transition are essentially the standard X-ray of atomic transition, but proportional to the mass, the mass of the captured particle. So these X-rays are different from antiproton and respect to anti-deuteron. And then at the end of the capture, the number of charged pions that are produced for an anti-deuteron is twice the number of pions that are produced during the annihilation from antiproton. So this is the planned gaps experiment. This is quite complex since they want to measure with the same detector few keV X-rays and large energy deposition of MeV, of the order of MeV, of stopping antiproton or stopping anti-deuteron, stopping antiproton. So this is quite challenging, and they will be launched with a balloon next year. And then let me talk about a possible new signature for anti-deuteron, is the presence of metastable states in helium. We know that in matter, lifetime of stopped antiproton or anti-deuteron is of the order of picoseconds. Instead, in liquid and gas helium, we have observed since 1991 delayed annihilation of the order of microseconds. What happens? The antiproton will be captured by the helium, removing one of the two electrons. And then it starts orbiting the system at quite a large principal quantum number level, that is the level with a similar binding energy of the ejected electron. Then, why helium is so special? Since we have only one electron, the Auger decay is suppressed, since we have a larger energy space for the remaining electron respect to the small energy spaces of the jump of the orbiting antiproton. So only a radiative transition remains, and they are slow. So this is the nature of this metastability. Moreover, the remaining electron will provide a similar to a screen respect to the collisional Stark effect that will provide atomic disexcitation channel for example, in hydrogen. So this effect is not really new. Similar effects are already proven and used by the Asakusa experiment at CERN. So this is what happened during the annihilation. A large fraction of annihilation is prompted, the annihilation is immediately. And then there is a small tail with a fraction of delayed annihilation. This effect was tested also at room temperature, at different gas pressure, and we expect a lifetime that is increasing with the reduced mass. This is the effect measure for negative pion, for negative counts. This is the measurement of different component for antiproton, and we expect a larger effect for anti-deuteron. So the idea is to use a helium gas scintillator within a vessel. We made a jet force simulation with a spherical vessel of 45 centimeter radius, containing a helium at high pressure. And this is surrounded by 3 boxes of time of flight scintillator. So this is the possible particle identification by the timing of the tracks. In yellow, we have the prompt hits that are occurring within few nanoseconds. And in magenta, we have delayed hits that are producing after the delayed annihilation. So stopping proton and stopping anti-deuteron will provide only a prompt track. Fragmenting nuclei will provide many tracks, but all of them have prompts. Instead, stopping antiproton and stopping anti-deuteron will provide a stopping prompt track and followed by several delayed tracks. So with the timing of the tracks, with the energy released in the time of flight, with the velocity measured by the time of flight, with the two energy measured by a calorimeter, that is prompt energy and the delayed energy, and event topology, we can distinguish, we can separate the signal from the background. This is one example of giant force simulation with stopping anti-deuteron, stopping antiproton, and fragmenting carbon. In the first few nanoseconds, we have just a prompt track from anti-deuteron, prompt track from antiproton, and a lot of fragments from carbon. Then, after few nanoseconds, the slow particle will be stopped, so antiproton and anti-deuteron will be stopped in the helium calorimeter. Nothing happens for the carbon. Then, after several nanoseconds, nothing happens. Anti-deuteron and antiproton will orbiting the helium in the metastable state. Then there is the annihilation that is providing quite a number of charged pions, both in anti-deuteron than in antiproton. Obviously nothing for carbon. Then just some small nuclear processes happens later. And then this is the typical helium calorimeter signature for antiproton and anti-deuteron. We have S1, that is a prompt, this blue one, the prompt signal that is related to the kinetic energy deposited of the particle that is deposited in the helium calorimeter. So the amplitude is proportional to the energy. Then after few hundreds of nanoseconds, we have a much larger delayed S2 signal. The amplitude of this signal is twice for anti-deuteron respect to from antiproton, because anti-deuteron will provide twice the number of charged pions. And this signal is not related to the kinetic energy of incoming particle. So we can have a very good antiproton respect to anti-deuteron separation. This is very simple, using time of flight velocity. For a fixed kinetic energy of the particle, S1, we have a much larger velocity in the antiproton with respect to anti-deuteron. Or, since the energy loss in the time of flight layer is inversely proportional to the velocity, for a fixed kinetic energy, we have a much larger energy deposited by anti-deuteron, that is heavy, with respect to antiproton. Then combining this information in the energy loss of an energy classifier respect to velocity of an energy classifier, we have a very good separation of antiproton from anti-deuteron, so the same of deuteron from proton. But we have also the delayed signal. Also in this case, we have plotted a time of flight delayed activity classifier that is combining the number of delayed hits, the energy of delayed hits, as a function of the S2 signal, that is delayed energy measured by the helium calorimeter. So you see that antiproton will provide less number of tracks with less energy deposited in the calorimeter. Anti-deuteron will provide a larger energy. So combining these two independent classifiers with prompt signal and the delayed signal, we can make cut and detect one anti-deuteron over 1000 antiproton. So this allows to measure anti-deuteron flux down to these 2 × 10⁻⁶ level without proton background. These are the antiproton acceptance and anti-deuteron acceptance as after these cuts, and then these are the planned sensitivity. In this plot on the left, we have the models from secondary anti-deuteron of astrophysical origin, and in red, this model of dark matter expected signal in case this bump on antiproton are real. And you see that this is the limit of best polar 2 experiment, the only one that we are still waiting for publication, we know. These are the expectation sensitivity for MS. These are expectation for gaps. And this is expectation for the ADHD technique without proton background. And then all these planned experiment or running experiment are in the same ballpark. So we will say that in the next future, it is possible to test this possibility directly. On the other hand, also if we will not found, for example, anti-deuteron, this is the sensitivity of ADHD to anti-proton low energy anti-proton signal. So ADHD will provide very good measurement of anti-proton at low energy. Then let me show some slides about ADHD technological readiness level. So the main ingredient is the helium vessel. So the vessel sets, and the thickness of time of flight sets the energy windows that for the ADHD is 50 to 150 MeV over nucleon. In particular, particles with energy lower than 50 MeV over nucleon cannot cross the thickness of the material and cannot enter in the active helium part of the detector. On the other hand, the pressure and the radius of the vessel will set the upper energy threshold, since a particle with an energy much larger than 150 MeV will cross totally the detector without stopping in the helium. So we need a light and thin vessel filled by high pressure and with larger dimension. So this is also a safety concern, since the gas stored energy in ADHD is similar to 4 kilograms of TNT. But no problem, this vessel have been tested also at 900 bars. This is a test of explosion of the vessel by the burst. And this CoPV is carbon overwrapped pressure vessel is a commercial product. This is an example of Faber company that is in Italy that is providing such a vessel that is used for hydrogen fuel. Then the helium calorimeter uses helium as a scintillator, and the helium has a very good scintillation property, has a very fast component of 10 nanoseconds with a very large number of photons released for each MeV, but the scintillation in the vacuum ultraviolet. So we need a shifter to measure the light with standard detector. So we want to use a silicon photodetector inside a high pressure vessel because PMT is very difficult to use at high pressure. So this is a prototype. Arctis, maybe if you are visiting TIFPA in the last period, you will see this pipe. This is a prototype that is produced for a neutron detector. It's a 50 centimeter long and is filled by 200 bar of helium-4. We have 2 light guides, sapphire, and 2 PMT on the 2 sides. And with this prototype, we already make some preliminary measurement of muons crossing the helium with the released energy of just 200 keV, so quite a small energy range. And then we have a preliminary measurement of very good time resolution and a very good energy resolution, also of this very low energy released. We also have tested a very thin time of flight bar with proton beam with muons, and we already have very good energy resolution and very good time resolution. So we expect no very big problem from time of flight. But now let me show some development we made at TIFPA. We construct a new silicon photodetector array for the photon detection to use this pipe, this detector, at the proton test beam. We want to test the detector with protons from 60 to 75 MeV that can can be stopped inside the helium gas. But the problem is that we have to replace one PMT that will be crossed by the beam. So we construct this, maybe some of you have seen on TIFPA, this detector that is an array of 8 silicon photomultiplier, 6 times 6 square millimeter, with a hole in the middle, so the beam can enter this pipe and cross all this detector without interacting with the silicon photomultiplier, and can enter in the helium. So we are planning to test this detector at the proton therapy TIFPA when this emergency situation will finish. And then now, in these days, this detector is in acquisition at TIFPA. I put this in vertical direction with a plastic scintillator on the top, with another plastic scintillator on the bottom, and then we are measuring crossing through muons, releasing about 3 MeV in the detector. So the acceptance is very small. I collected 50 events since 27 of March. And the analysis that they're taking is ongoing, but all is working. This is the shape of a typical pulse on the silicon photomultiplier array. Is quite fast rising time. This is the shape of the scintillator, helium scintillator PMT is in bottom, and this is the shape of the PMT on plastic scintillator. So I am arrived. I will say that ADHD is a new technique for anti-deuteron identification in helium target, and is a promising tool for dark matter search. This is our website of this project at TIFPA. So if there are students, I encourage to contact us for stage. We will shoot protons in the helium pipe very soon for thesis, or also for a PhD project, joining the analysis of anti-deuterons from AMS and this development of ADHD. So, thank you very much. I almost used all my time, and then I can, if there are questions, I can stop share.